All right, let's go and review some things we've been working on recently. Last night you looked over chapter 3 and we're reviewing. There were really 4 principles that I want to highlight here in chapter 3. And the first was Pascal's principle. Kendall, what did Pascal's principle say? What did it deal with?
Pressure.
What about pressure? Pressure within what?
Liquid.
Specifically, a liquid that is... Audrey? Confined. He specifically dealt with the confined liquid. So that's, if you're trying to associate, if you remember Pascal, now granted his name is the unit for pressure. But you want to remember Pascal, confined liquid. What did he specifically say about a confined liquid? Back to you.
Force per unit area.
Well, yeah, pressure is force per unit area, but within a confined liquid, what did he say was going to be true about pressure?
Oh, it's going to be normal.
Back to Audrey.
Equal interaction.
It's everywhere the same. So the depth normally affects pressure, right? Liquid pressure depends on depth, but not in a confined liquid. In a confined liquid, pressure is everywhere the same anyway. Then we had another guy, Archimedes. What did Archimedes' principle deal with?
The water you displace is equal to your weight.
Oh, try it again. You got the terms in there, but you're right. There's something about displaced liquid or displaced fluid, right? And there's something about weight.
Buoyant force.
Buoyant force is good in there. Okay, so Archimedes think buoyant force or floaty things, right? Archimedes buoyant force, and he said the buoyant force
is equal to the weight you displace.
the weight of
The displaced liquid.
weight of displaced liquid, weight of the liquid you displaced. There we go. Good. So we had all the right terms. We just had to put them in the right order. So going back, Pascal class dealt with confined liquid. In a confined liquid, pressure is the same everywhere. Okay. Archimedes dealt with buoyant force, and he said that buoyant force equals
The
weight of liquid you displace or thing displaces. Then we had another guy yesterday. We just talked briefly at the end, and it was Bernoulli. And Bernoulli, what did we say about Bernoulli's principle?
There's an inverse relationship between lateral pressure and velocity.
Wow, that was really well stated. All right, there's an inverse relationship between lateral pressure and velocity. Excellent job, exquisite. All right, great job, good job. No, I applaud it. Good. The faster the liquid goes, the less sideways pressure you can put on the wall of a pipe or on the wall of the hose. So remember we said, as long as the water's flowing really well, you're not going to get a big issue with the leak out the side. In fact, you wrap duct tape around that hose, you're going to be fine. If the water sits, maybe you're not spraying the water and you're letting it just stop, that's where the pressure is going to build up, and it might blast your piece of duct tape right off the side of the hose. Then there was another principle. It wasn't named for anybody. It was the principle of continuity. For instance, the continuity of your relationship with your siblings is inversely proportional to your use of the principle of continuity. What was the principle of continuity? Volunteer. Volunteer for principle of continuity. Okay, back to the garden hose.
The area and volume of something can be equal to the area and volume.
Not area and volume.
Viscosity.
Not viscosity, the other V.
Velocity.
Velocity, okay.
Another one. So they can be equal.
They can be equal, so Michael,
They always stay the same.
Yeah.
what stays the same?
The area and the velocity.
The product of them, right? So we could say the volume flow rate, but practically speaking. So let's just real practical. We got a garden hose. We have a younger sibling. What do we do?
Spray
How?
hard.
How? How do you get to spray hard?
You narrow.
You narrow.
Oh, so narrow, help them out here, Kendall. Narrow meaning if we shrink use the word she used, shrink the cross-sectional area, what happens?
It goes faster.
So using that V word she finally remembered. Velocity increases. Yes, you shrink the area, you're going to get a greater velocity, right? Because the volume flow rate's constant, but area and velocity, they're, again, inversely related. Shrink the one, increase the other. Also pressure washer and cap. All right, so we had some equations in this chapter. Let's go way back to the beginning of the chapter real quick. Way back to the beginning of the chapter real quick. And the very beginning of the chapter, our first equation was actually the definition of pressure that Kendall gave a moment ago.
P equals F over
There we go. And then we talked about the law of liquid pressure, Audrey.
P equals rho GH.
And then, Michael, we said that that shows why pressure depends on depth. Then we said if we wanted to find how much force bears down on the bottom of a container.
F equals A rho GH.
There we go. We also said, though, that since force exerted by a liquid class is what direction?
Normal.
Normal to every surface, then it also pushes on the sides of the container, and so we could find the force on the side wall of a container, Audrey.
1/2 A rho GH.
Or we could find average pressure on the side of a container. Kendall?
1/2 mg.
And so all of these equations kind of came together all at once. Then we talked about Pascal's principle, right? The confined liquid, and we talked about a device that uses confined liquid and this equal pressure everywhere to actually multiply force. Michael? Hydraulic device, right, with an AU for the ah sound. And there were two equations for the hydraulic device. Do you remember one of them, Kendall? Michael? Pressure is everywhere the same in the confined liquid. Does that help?
Yes, but it's like F over A. 1 F1 over A1 plus F2 over A2.
There we go. Yeah, the pressure of the F over A is everywhere the same. Though we said that instead of A, we could substitute what, class? The diameter squared. Again, it's not the same thing, but it's usable in that equation. So it's not even approximately equal, but it's an equivalency we can make as far as the math is concerned. Because, why, Audrey? Why does it work? Anyone? I said we couldn't do that in one of these equations, but I could do it here.
Because you can cancel out the A's here.
Yeah, there's an A on both sides, so technically it equals a fourth pi d squared, but the 1/4 and pi's cancel when there's an A on both sides anyway. So that's why we can make the substitution. And we said we don't get something for nothing though. In a hydraulic device, you gain force, but class, you lose distance, don't you? You'll lose distance because the volume doesn't get lost. The volume stays constant, so whatever volume of liquid you push is the volume of liquid that pushes for you as it transmits your pressure for you. And so what equation shows the volume staying constant, Audrey?
Say A1 H1 equals A2 H2.
There we go. That's a 2, not a Z. We're once again, the diameter squared can be substituted here because area times height is volume. From there, we talked about Archimedes' principle, right? And I said that when you boil Archimedes' principle down, it basically is this. What determines whether or not an object floats, class?
Buoyant force.
Density. Now, the buoyant force is what causes the floating, but buoyant force may or may not be strong enough to make something float, right? Everything gets buoyant force, but is the buoyant force enough? Well, it depends on the density, right? And we looked at bowling balls in a video and Coke cans and cool stuff like that. And you have a pool at your house? You have a pool? Okay, you don't have a pool. All right, so next time you chuck Coke cans in the pool and have siblings go get it. Be like, tell you what, I'll get the Diet Coke and you get the Cherry Coke. Ready? Throw them in at the same time. Go! And you go swim to get your Diet Coke and they dive down to try to get their Cherry Coke and you're sitting there waiting for them. And then if you're Michael, you drink the Diet Coke, and if you're not Michael, you drink the Cherry Coke they brought out of the bottom. Anyway, evil tricks you can play on younger siblings. Knowledge is power, right? It says so in the back of the room. All right, that's right there. Yeah. Anyway, sticking your finger in an outlet would give you some knowledge. It's the wrong kind of knowledge. You better have knowledge without sticking the finger in the outlet. I do not advocate that. Actually,
My little brother did that.
I saw this meme, it was like a year ago. And you know, back when the hot topic was like socialism in the United States, Bernie Sanders was running for president. This may be a couple years ago at this point. And the people that, look, socialism does not work. Look at every nation that's tried it. It does not work. It destroys the economy. And but they didn't do it right. They didn't actually, their version of socialism wasn't executed properly. And so I saw this meme, it was a person getting ready to stick a fork into an outlet. It's like, yeah, I know everyone else has failed with this, but they didn't do it right. Now the point is you're going to fail. The whole ideology of socialism is wrong. And And so Facebook said that I was promoting violence or something with the meme, and I was giving bad ideas to young people, so they took my post down. Anyway, they waited a year to take it down. They're like, we found a problem with your post, and they took it down. So anyway, I do not advocate sticking your finger in an outlet to gain power. I'll tell you. Back to Archimedes' principle. Floating, right? What determines whether or not something floats, we said? Density. So we have two equations. One is for the buoyant force, Michael, and the other is for the weight of the object. And the cool thing is, they're the exact same formula. What is the formula, Michael?
That's a good question.
It is a very good question. All right, Kendall? Rho VG. Not Roe v. Wade, but Rho VG. That helps you remember, I don't know. The difference is for buoyant force class, we're looking at the density of the buoyant force. What causes buoyant force? The liquid has the buoyant force. It pushes, right? So the liquid's density. For weight, we're looking at the object's density. And we just compare the two numbers. And when if the weight comes out greater, then it sinks. If the buoyant force out greater, buoyant force comes out greater, then it floats. And it would tell us, if we saw the difference, how much could be supported by said floating object by buoyant force. We talked about the principle of continuity next, and we had an equation that Audrey was trying to describe to me a minute ago. Let's go to Kendall, though. Kendall, what is that equation for the principle of continuity?
A1 times V1 equals A2 times V2.
And once again, we can substitute a diameter squared for the area, and we see that the area and the velocity product is constant, and we did not have an equation for Bernoulli's principle. This idea of the principle of continuity, or even Bernoulli's principle, had liquids in motion. Liquids were moving, right, for them to be applicable. And what is that term that describes liquids in motion, or the study of liquids in motion, Kendall? Hydrodynamics. We said, here we go, Audrey, here's your word, that liquids in motion generally resist motion to some degree because of adhesion and cohesion. And this term is viscosity, the reluctance to flow. So we have velocity, volume, and viscosity. We said, though, for our purposes, for the principle of continuity to be accurate, that we can't deal with viscosity or other factors, in fact. So we said what we're going to say is that this works if we have something called an ideal liquid. There were three characteristics, not a long list, only three things that we need for a liquid to be ideal. Give me one of them, Michael.
It is not subject to viscosity.
No viscosity, okay? Non-viscous. You took the easy one.
Density.
Okay, the density has to be the same throughout, so we'd say uniform density. Incompressible, very good. Can't be compressed or squished. Okay, so those are our three characteristics of the ideal liquid. Your homework dealt with this problem here, or homework problem dealt with this equation here. Page 48 in your textbooks, problem number 10. And go ahead and read problem number 10 for us, if you would, Kendall.
Water flowing with a velocity of 1 meter per second in a 3 centimeter diameter pipe enters a short section having a diameter of only 1 centimeter and a section having a diameter of 5 centimeters. Calculate the velocity of the last two pipes.
Alright, so we got 3 centimeter in diameter, and the pipe's going to narrow down to only a single centimeter diameter, so a nice narrow piece of pipe, and then it widens back out to 5 centimeter diameter. This is maybe a little exaggerated here, maybe something more like that. But it widens back out to 5 centimeters. And the question is, how fast is the water going to go through each of these sections? 3 centimeter, 1 centimeter, and 5 centimeter. And of course, it tells us one of the sections, the starting section, right, is in the 3 centimeter pipe, the water is flowing at a rate class of 1 meter per second. All right, so when we plug it into the equation, because there's 3 sections, we'll tack on an A3, V3. And again, in each case, instead of area class, diameter squared. So we take the diameter squared right here, 9, times the velocity is equal to diameter squared times the velocity, which we don't know, times equals diameter squared, 25 times velocity.
Don't know.
We don't know. All right, this is perhaps the easiest section to solve for, class. 9. Yeah, 9 times 1 is 9, divided by 1 is 9, right? So 9 meters per second, I think, is it 2 sig figs? Yeah, 9.0 meters per second. There's our first answer. How many had that for the 1 centimeter pipe? And then the 5 centimeter wider pipe, here, ignore this, and solve that equation. And what do we end up with for our velocity in the wider pipe? Audrey? Uh-oh. Did you forget to square?
No, I actually put 2 3s instead of the 5 centimeters, so I got 27. 225.
Uh-oh. Careful. How do I solve for the v sub 3?
You
I divide. I multiply the 9 and 1, of course, to get 9, but then I divide the 25 to get
2.7.
9 divided by 25? I think you do 25 divided by 9. 9 divided by 25.
0.36.
0.36 meters per second. And again, the nice thing is you can look at your answers and check and see if this makes sense. Okay, it's flowing along at a meter per second. What should happen when the pipe narrows, class?
Faster.
Should go faster. Did it go faster? Yes. And then when it widens, what should happen? Slow down. In fact, it should slow way down. It should slow down more than this, right? And it does with the 0.36. So you can just follow the math, 9 times 1, 9, and then divide away the 25 from both sides. And again, probably a good idea to go ahead and do the physical moving, dividing, things like that. Questions on this? Anyone get both of those answers correct? Okay, good questions. Let's take a look at some math problems here on the screen. And you can set your books aside, just have out your... Did she have her name be mute this whole time? She did. Oh, bless her. Or did I do that? I don't know. I lose track. All right, so I got some problems for you here. And go ahead and take just a moment to work this problem. Yes, sir.
Do you want 2 or 4 sig figs? Because we don't use water.
Well, we're using seawater, so we're using 4 sig figs here. We're also using this number. So how many sig figs are we allowed? 2. Right, we always go with the lowest possible number. This is 4, this is 2. The 9.80 was 3. We have to go with the least number. So we are going to round our answer to just 2 sig figs. Probably scientific notation is best here. All right, what is our equation to find the pressure on this submarine? Kendall? P equals rho GH. So in for the rho, of course, that's the 1,027 kilograms per cubic meter. We said G. Now technically, G is going to be a lot stronger down there. It's not going to be 9.80. It's probably going to be around 9.85, 9.86. It's going to be stronger. But for our purposes, we don't want to have to think through those details and make estimates that are flawed. So we'll just say 9.80 because it's what we do. And then for the H, that's where we're going to plug in the 11,000 meters. So we're going to get a huge number here, and definitely going to go scientific notation. Yeah, for sure. And what do we get for our answer here, Kendall?
1.1
Good. We'll round off to, as we said, the 2 sig figs, so 1.1 E8, and pressure measured in pascals. How many have the 1.1 E8 pascals? Good. All right, questions at all on this problem? All right. You know, the last statement's a bit of a stretch. It's definitely not the Chattahoochee. Have you ever been swimming in the Chattahoochee? We took the kids swimming in the Chattahoochee. That was interesting. Not like right where the white water was. downriver from here.
If you go whitewater rafting, they actually let you go swimming because it has a natural lazy river.
Around the little, there's a little.
Yeah, there's a little bend, and you like get out of your raft, and the diver person, whatever, the guide takes the raft down to the end, and you jump in the lazy river and you get out. It's pretty fun.
I also have a problem with this. A picture may help you think it through if you're struggling. All right, what equation are we going to need to use for this problem, Michael?
P equals 1, or F equals 1 half A rho GH.
Good, F equals a half A rho GH. And for the most part, this is really easy to plug in, right? We've got the half, the rho class we're going to say is 1,000, the G we'll say is 9.8, the H we'll even say is 18, though we could go ahead and take half of the 18 now if we wanted to. And since we're averaging half the height, would give half the force. But we need to figure out the area of the wall of the dam. And so we're looking at it from the fishy perspective. Here's the side of the river and the other bank of the river. It's 18 meters deep. Okay, that area goes all the way to the top of the dam. I don't know. But 18 meters deep is how deep the water's going to go. And the dam stretches a width of 42 meters from side of river to side of river. If that's true, how would I find the area that the water is pushing on, class? Yeah, length times width, the 42 times the 18 to get 756. All right, so there's the cross-sectional area we're going to use. Obviously, the 1,000, the 9.8, and the 18, take half of all of that, or take half of the 18 right up front to get the 9. And we multiply all those numbers. We get how much force pushing on the wall of the dam. Michael?
6.77.
Good, 6.667, blah, blah, blah. I'm going 2 sig figs. We'll say 6.7 E 7 newtons, because it's force. And there we go. How many have that answer? All right, questions on that? Again, just a quick picture may help to we figure out, well, what is the area I'm doing here? Well, it's the same 18 that is the depth. We're using it again because it's a side. Whereas like a bottom, you wouldn't use the height to calculate the area of a bottom. But the area of a side wall, you would. All right, questions on this one? Let's take a look at another one here. 2 problems here, kind of built into one, so solve both parts. That's your seats. what's the first equation we need to use here, Audrey?
A1H1 equals A2H2.
Okay, we could actually do that one first if we wanted to. Where again, instead of the areas, we're going to plug in
4 and 100, or the diameter.
diameter squared, right? So d squared, 1 squared here, d2 squared here. So for the smaller piston, we square its diameter, we get 4. And we're going to multiply that by the height or the distance that the piston moves. 12 centimeters. And we got the area or diameter squared rather of the other piston, 100, and we're finding h sub 2. So you're actually finding the second answer. How high will the other piston lift the object? And what did you get for h sub 2?
0.48 centimeters.
There we go, and that's 2 you need 3 sig figs, so 0.480 centimeters. All right, good. So the guy pushes down 12 centimeters, it pushes up half a centimeter, okay? Do we get that for the second answer? What's the other equation needed here, Kendall?
F1 over A1 equals F2 over A2.
There we go. And again, if we assume the 1 is for the smaller side where the force is put in, it tells the force that's put in
200.
200 newtons. And again, instead of area, we'll do diameter squared, so 4. And then we don't know the force that lifts up on the other side, but we do know cross-sectional area, or diameter squared at least.
100.
100 again. And then we'll cross multiply. Again, we would technically have centimeters squared, they would cancel anyway. And what do we get for the force that lifts up on the other side, Kendall?
5,000 newtons.
Yes, 5,000. Oh, that's, I need 3 sig figs. That's 1.
Okay, that's
Well, if I can't put it somewhere, it has to be, that's the only place I'm allowed to put a decimal, but that's 4 sig figs. Oh, what do I gotta do?
scientific notation.
Yeah, scientific notation.
5 decimal degree.
Well, and that's 1 sig fig. How do I get 2 more sig figs?
Put 2 zeros.
There we go, 5.00E3 newtons. So put in 200 newtons, get out 5,000 newtons. Put in 12 centimeters, only get out 0.48 centimeters, and we see the trade-off here. Do we get these 2 answers? Questions on this? All right. There we go. Yes. what two equations that really feels like one equation do we need to use here, Michael?
FB and W equals rho E G.
There we go. And so we're going to take the density of the water, we're going to take the volume that the raft displaces, which is its volume, times gravity, and that'll give us how much buoyant force is going to lift up on the raft. What did you get for the buoyant force that lifts up on the raft, Michael?
The buoyant force of the raft, 20, no,
That's the weight, that's what I'm getting to in a minute.
33,429.76.
There we go. I didn't sign the invitation, but 320 something-ish, I don't know. And then for the weight of the raft, what did you have, Kendall? So taking the density of the raft itself, the volume, of course, of the raft, and gravity. Yeah, this is 3.342, and I just had ... after that, E4 newtons, so I didn't have the actual number either.
2.5584 either.
I got a 2.507 ... E4 newtons. So when you take the density, which is 750, right? And we're going to multiply length with height to get volume, and then gravity.
That's what I
Ah.
Yeah. I forgot that you got it.
Okay, so now you have the 2.507 E4. Okay, do we get these numbers now? Everyone good on these numbers? All right, so if it asks how much what load can we put on the raft, what do I need to do to finish it, Audrey? Just subtract this number, the buoyant force minus the weight, gives the weight of a load that could be placed in addition to the weight of the raft itself. And what do we get for our final answer? Anyone?
I got 8,400.
Yeah, rounded to 2 sig figs. I have 8,400 newtons or 8.4 E3 newtons. Questions on that? So that's around a ton like we had on a similar problem in the textbook. I think it was a cedar raft. This is oak, but similar questions? All right. One more. Were y'all here when they had the field day where the fire truck came and they sprayed the field and sprayed all the little kids on the, were you the little kids on the field or were you working it?
I was a little kid.
You were little kids when they sprayed everybody and everything, and there was water everywhere, and we kept having to move where the awards were being held because the water kept coming. And, yeah. So obviously where it connects to the hose itself, right, connects to the fire hydrant, and then they have the sprayer nozzle that narrows it down. What's the speed as it comes out of that nozzle? What equation do I need this time? Kendall?
A1 times B1 equals A2 times B2.
There we go. And for the A's, again, we're going to square the diameter. So the first A1, we plug in 100, the 10 squared, times the velocity of 15 is equal to the next diameter squared
16
times velocity 2. We multiply, we divide, and we end up with what?
93.75.
Good. Round it off to 2 sig figs?
94.
94. That's a velocity or a speed, so meters per second. Which, I mean, think about that. The P field's about 94 meters long-ish, close to it. So that would be the water getting from the hose all the way across the P field in just a second. Blasting pretty hard, if those numbers are right. I don't know if they are for sure. All right, how many got the 94 meters per second? Any questions on the math from chapter 3? Because this review kind of covers it all. Any questions? All right, clear desk, except for a clean sheet of paper. Clean sheet of paper and a pen and a pencil. Clean sheet of paper and pencil. Actually, let's take this in pencil since there's some math, and that'll help us in case we do happen to make errors. Not that we like making errors, but they happen. Random errors. Unless you're using the wrong equation, then it's not random error, class. It's systematic error. Yeah, put a decimal in the wrong spot. Okay, random error. Wrong equation, systematic error. Forgetting to square, systematic error. Right, Michael?
Pencil breaks in half.
Pencil breaks in half, random error. Keep using pencil that's broken in half but doesn't write, systematic error. Anyway, all right, first last name at the top of your paper. Don't put your name as error. Okay, first last name at the top of your paper along with today's date. Today's 8/31/22. 8/31/22 is today's date, and this is quiz 4B. We took quiz 4A a little bit ago, so you knew there was a B coming. Here we go. Alright, just take a look at the quiz together very quickly. 1 through 5, completion, write the word or the words that complete the statement. Number 6, listing all 3 of those things. And then 7 and 8, a couple of problem solving. And then we've got a bonus for you as well. Alright, you may begin, and we'll end the video here.